Hi, so welcome to this next session where we're thinking about risk of bias and design justification. And in this particular session, we're going to look at the risk of bias in stepped wedge cluster randomized trials. So quick recap then, thinking about where we've got to. So we've heard that the stepped wedge trial is becoming increasingly commonly adopted. And it shares many characteristics in common with the parallel cluster randomized design, especially other repeated measures cluster designs. But it also brings around some significant complexities. So I've listed three here that are probably the most important three. So these are temporal confounding, within cluster contamination, and deviations from the randomization. And in this section, we're going to look to understand how these additional complexities can lead to bias. So our objectives here are to consider formally the additional risks of bias associated with a stepped wedge cluster randomized trial. And we're going to look at these in order of their likely importance. So starting first with temporal confounding, moving on to within cluster contamination, and then finally looking at randomization biases. We're also going to consider other cluster randomized crossover designs, so the multiple period cluster randomized crossover design, for example, and we're going to have a look at some case studies. So as a recap, these are the risks of bias as outlined by the Cochrane risk of bias tool for parallel cluster randomized designs, and remembering that there are 5 domains. And we've looked at some of these domains already, particularly thinking about how they might increase the risk of bias in parallel cluster designs. And then we also looked at this additional domain that we have termed domain 6. And domain 6 is thinking about analytical biases. So as a quick recap then, analytical biases, they essentially refer to the need that the analytical approach should give us unbiased estimates of the intervention effect. And so this means accurate estimates of the point estimate of the treatment effect and its standard error. Now there is an additional complexity in stepped wedge trials, and that is that these measurements are taken repeatedly over time. And so the within cluster correlations that we need to allow for are probably more complicated than the simple exchangeable correlation structure that we typically allow for in a parallel design. And in session 4, we're going to think about making sure that we allow for these more complex correlation structures in order to get unbiased estimates of the standard errors of our effects. But we'll be looking at that in another section, and we'll put that to one side in this section. So when we're thinking about risks of bias in stepped wedge trials, we can think about the first bias as a bias arising from an imbalance over time between control and intervention conditions. We're going to refer to this as temporal confounding. And this is going to be categorized under domain 6 as a type of analysis bias. We're then going to move on to think about biases due to deviations from the intended intervention. So this is domain 2 in the ROB tool. And this is thinking about within cluster contamination and carryover effects. Then we're going to move on to think about biases arising from the randomization process. So this is domain 1A. And thinking particularly about non-adherence to the randomization schedule. So over the next few slides, we'll look at each of these in turn. So first of all, why is time a potential confounder? So as a recap, a variable is a confounder or a covariate is a confounder if it is associated with both the treatment and the outcome. Now in a stepped wedge cluster randomized trial, time is a confounder because the likelihood of being treated increases with calendar time. So as calendar time increases, the likelihood that an observation is treated is greater than in earlier calendar time. Now, if the outcome changes over time too, in absence of any intervention effect, so this might represent a regular secular trend, then because time is associated with both the treatment and time, then time will be a confounder. So here's an example to illustrate why time can be a confounder in a stepped wedge trial and its potential importance. So these graphs represent the results from a stepped wedge trial where there is probably an underlying secular trend. So the trial in question aimed to increase the percentage of women who received a membrane sweep after exposure to the intervention. So the percentage of women who received a membrane sweep were compared between the intervention and the control participants. And it was identified that the unadjusted relative risk was 1.06, suggesting an increased risk or likelihood of having a membrane sweep on exposure to the intervention condition. It was in fact not statistically significant, but we'll just keep our eye on the point estimate. So an apparent positive effect of the point estimate. However, this design was a stepped wedge cluster randomized trial. So the black in this plot here represents what we might call the secular trend in absence of the intervention. So what's happening to the percentage of women who were swept in absence of the intervention in the control clusters as a function of calendar time, week of the study. Now we see here that there's a significant and continued positive trend. So the percentage of women who are receiving a membrane sweep gradually increases over the weeks of the study. And remember, this is an absence of the intervention, so this has got nothing to do with the intervention. This is just in the control clusters. The red is the model-based, time-adjusted effect of what's happening in the intervention clusters. And it turns out that the adjusted for time relative risk is 0.88. Again, not statistically significant, but focusing on the point estimate, this adjustment for time reverses the apparent direction of the effect. So ignoring the secular trend, it looks like at the point estimate there's an apparent positive effect. After we allow for the fact that there is a secular trend, the adjusted point estimate reverses the direction of the effect and suggests that on exposure to the intervention, things got worse, not better. So this example here illustrates how secular trend can be an important problem in stepped wedge trials. So this means in order to be able to estimate how our treatment effect or treatment is working, we have to use a model-based analysis. And we have to adjust for underlying secular trends. And we do so by assuming that all clusters follow the same secular trend. So in this graph on the left-hand side, we've got three clusters, cluster 1, cluster 2, cluster 3. The black lines represent the underlying secular trends across these three different clusters. So this black solid line here represents what's happening over time in one of the clusters. This other dashed line represents what's happening over time in the second cluster, and then our third cluster here. So these are our underlying assumed secular trend. Now, in order to model our stepped wedge data using the models that we're going to look at later, we almost always assume that the secular trends are common between all of the clusters under the control condition. Now we allow for there to be shifts up or down on our x-axis here, but the underlying assumption is that they're all following the same shape. So all the clusters are assumed to follow the same trend pattern. We also assume that there's a common intervention effect. So by this we mean that on exposure to the intervention condition, all of our clusters shift up by the same constant amount over the entire study period. So these are the model-based assumptions that we typically make when analysing data from a stepped wedge trial. So what does this mean in practice? So in practice, it means that the analysis is complicated by the fact that changes over time can occur. These are called secular trends, and these may confound the intervention effect. So an apparent effect due to the intervention may in fact just be due to a natural change over time. So we have to rely on a model-based analysis. But most model-based analysis assume a common secular trend. Now, this is unlikely to be tenable in many situations, and we can't test it in the data that we have at hand. And it's worth noting that these types of biases are unlikely to affect parallel designs. So how can we prevent these temporal biases? Well, at the design stage, if we randomize a large number of clusters, the different trends will probably balance across the sequences. We can also think about including more homogeneous clusters to meet the assumption of a common secular trend. At the analysis stage, we have to allow for secular trends. We have to think carefully about the model choice. We also have to appropriately model the correlation structures. So I've just put that on here as a reminder that correlation structures are more complicated here. But failing to model the correlation structure properly usually doesn't give us a biased estimate of the treatment effect, just biased estimates of the standard errors. Can time be a confounder in a cluster randomized crossover design? So if on the left-hand side we consider a cluster randomized crossover design, we've got two sequences. In the first sequence, clusters are observed for 4 periods under the intervention condition. They then transition to the control for another 4 periods and so on. And in the second sequence, the reverse happens. So in the first 4 time periods, the clusters in the second sequence are under the control condition, and then they switch over to the intervention condition. So if we look down our design at any particular point in time, for example, in these first 4 periods here, we see that there's a balance of intervention control conditions. So we have 10 clusters in the intervention, 10 in the control. In the second 4 periods, we've got 10 clusters in control, 10 in the intervention. So this design here on the left-hand side represents a design that's balanced on time. So time wouldn't be a confounder in this type of design here. Now that's how cluster randomized crossover designs are designed in theory, but in practice they often end up looking more like this. So clusters are allocated to sequences that rotate between intervention and control condition, but they initiate these sequences as and when they're ready to be ratified in the trial. Now this can mean that as we look down our design at any particular point in time, we might not have an even balance of treatment and control clusters. So although in theory these designs are designed to be balanced on time, in practice there often end up being some residual imbalance in these designs. So time can be a confounder in cluster randomized crossover designs, even when they look to be apparently balanced on time. To move on to the second type of potential bias that can arise in these cluster crossover designs, and this is biases due to deviations from the intended intervention. So within cluster contamination, sometimes referred to as carryover effects, refers to biases due to the way that the data have been collected under the control condition in a way that it becomes contaminated by the intervention condition, or vice versa. Now, this type of contamination or carryover effect can occur at 2 levels. It can either occur at the level of the individual or at the level of the cluster. So let's have a look at how it might arise when it happens at the level of the cluster. So observations collected under the control condition can become contaminated by the intervention condition if, for example, a provider is in a site that is in the control condition, but it, either deliberately or inadvertently, implements the intervention before the allocated time. And this would then represent a type of contamination or crossover effect at the level of the cluster. It can also happen the opposite way around. So for example, the provider is in a site that should have already crossed to the intervention condition, but that provider, for some reason, persists in applying the intervention condition. But within cluster contamination can also happen at the level of the individual. And it's particularly problematic in settings where the participants have a long exposure to the intervention. So take, for example, patients in an intensive care unit. So patients in intensive care units might have a prolonged stay, and they might still be in the intensive care unit at the time that their cluster crosses over to the intervention or the control condition. If they also have a prolonged exposure to the intervention, perhaps the intervention is a change in the way that the care is delivered, it then becomes possible that observations from individuals who have been included in the control condition might become contaminated with the intervention condition. Now, in trials where the participants have a short exposure to the intervention, these are sometimes referred to as continuous recruitment short exposure designs. This type of contamination is unlikely to arise. There are ways to prevent within cluster contamination, but it's also worthy to note that this type of contamination is unlikely to happen in a parallel cluster trial because clusters do not transition between the treatment conditions. Ways that we can try to minimize its impact are to add in transition periods, careful designs, so trying to prevent this control condition observation becoming contaminated with the intervention, or this intervention participant becoming contaminated with a control condition. Let's take a look at a real example. This is the PADIT trial. This is a cluster randomized crossover design. We've looked at this example before. Remember, there are 28 clusters in this design. The first 14 clusters have been allocated to the first sequence, where they spend 6 months under the intervention condition, then 6 months in the control, and so on. And the other 14 clusters are allocated to the dual of that sequence. So this trial was conducted across 28 hospitals. It included around 12 or 13,000 high-risk patients who were undergoing a commonly used procedure for a cardiac rhythm device implementation. So the control condition here was that patients received a single dose of preoperative antibiotics, and in the intervention condition, they received a strategy of incremental antibiotics. Now, contamination could have arisen here if participants were admitted soon after the transition period when the cluster had not fully transitioned. So, for example, maybe a participant was admitted during this period here. Their cluster should have transitioned to the intervention condition, but maybe that cluster had delayed the implementation of the intervention slightly for some reason. So there is some risk here that contamination at the level of the cluster or the individual might arise. And then the third type of bias is bias arising from the randomization process. So remember that sometimes non-adherence to the randomized allocation schedule might arise, perhaps because some clusters are considered to be more needy, and therefore it is considered that they should get the intervention first. Other times, it might be that clusters might be dissatisfied with the knowledge that they're going last, or clusters might join be randomized when they're ready to participate in the trial. So these are the sorts of biases that can happen with the randomization process in stepped-wedge and cluster paper designs. So imagine that we are in the setting where we are conducting the randomization for a stepped-wedge trial, and one of the local investigators might say that this cluster is really needy. We think that this intervention is going to be very beneficial. Can they please go in the first sequence? But of course, this would undermine the randomization. So there are prevention strategies to minimize these types of biases. So one prevention strategy might be, for example, to reveal the allocation as late as possible. This would prevent potentially disappointment at going last. But it might also be possible that it might be better to reveal the allocation as early as possible. This might prevent anticipation dropout. So it might prevent dropout because of an anticipation of going last. The other possibility here is to use these batch designs where the more needy clusters do go in the first batch, and this is properly accounted for, something that we'll consider in the next session. So let's have a look at the Care to Quit study. So remember, this is a stepped wedge cluster randomized design using a cohort sampling mechanism was an evaluation of a complex care pathway, which included things like champions. The cluster was a cancer care centre, and there were 9 clusters allocated to one of 3 different sequences, and here are the 3 different sequences. And there were 9 periods in the study. There were repeated measures. So this design used cohort sampling, maybe open cohort, it wasn't quite clear. And there was individual participant recruitment. And the outcome was smoking cessation, and it was collected specifically for the research purposes. Now, was care to quit at risk of bias? While thinking about randomization bias, there was no mention of any independent randomization. So potential source of bias here. Identification and recruitment bias. Well, there was direct participant recruitment, but it was unclear if there was post-randomization recruitment. There were lots of subjective eligibility criteria. Were there any deviations from the intended intervention? Well, the active intervention was not available in the control clusters, so probably no. Was there any potential for analytical bias? Well, time adjustment will be essential, but it will assume that all 9 clusters follow the same underlying trend. And whether that's a tenable assumption or not, we won't know. So summary so far then. So stepped-wedge trials and other multiple period cluster trials are subject to several risks of bias that might challenge the strength of evidence generated from them. One of them is within cluster contamination. Some of these risks of bias might affect some types of cluster randomized designs too, but some of them appear to be greater under the stepped-wedge design. And this is particularly the bias that can arise because of confounding of time by design. Therefore, it's probably the case that the use of the stepped-wedge trial must be very carefully considered. So here are the methods references and the study references that have been cited during this session. And up next, we'll start to think about when a stepped-wedge cluster randomized design is justified.